Welcome to corrosion. This homework problem is focused on, it's asking us how much current and how much potential do we need to apply in order to pull down the corrosion rate of a metal from 200 microamps per square centimeter to this reduced rate of 0.20 microamps per square centimeter. And so this helps inform my scale that I'm going to use. This axis is the log of the current density. I'm going to use units of microamps per square centimeter. And this value right here is 2 times 10 to the 2 microamps. So let's make this value right here 10 to the 2 microamps. Let's make this one 10 to the 3, 10 to the 1, 10 to the 0, 10 to the minus 1, and so forth. So 2 times 10 to the 2 is going to correspond to this current. And so what the problem statement has told us that without doing any polarization of the part, we have a corrosion rate of this value. So I'm just going to put a little dot there. Now, I don't know where to put that dot relative to the left axis, which is our potential axis, because the problem statement doesn't give us anything about potential except for the slopes of the lines by the Tafel constants. So I'm going to label this axis relative potential because I don't know the absolute potential. And so relatively speaking, I'll kind of make this quote-unquote 0. It's not actually 0 volts, but it will help me know how much polarization I need in order to protect the part. And now I'm going to do a little bit of hand waving. So I want you to understand the bigger picture. So I'm going to draw some lines in a couple different colors, and then I'm going to erase them. So the first thing I want to draw is the metal oxidation curve, and I'm just going to draw this with a somewhat random slope. So that metal is oxidizing, right? This is our metal oxidation line. We don't know what metal it is, so I'm calling it a generic metal M. And then the second thing we have happening is that we have some sort of reduction reaction like that. And so relative to the metal, of course, the metal, it would have an exchange current density. At that exchange current density, the oxidation rate is equal to the reduction rate, right? And similarly, for the reduction reaction, right, it would have an exchange current density, and it could be reducing. This is something, I don't know what it is reacting with electrons to make, I don't know what to say, X plus an electron to make X2. We don't know what the reduction reaction is, so I'm making stuff up here. But the point I want to bring to your attention is that is as follows. It's the intersection of that reduction curve, the blue curve, with the oxidation curve, the red curve, that gives us this unpolarized corrosion rate of 2 times 10 to the 2. And so what we need to do as our next step is we need to draw these two lines with the correct slopes using this 0.0, this point that I've put within a box as sort of the origin. And so what I'm going to do is erase all these lines, and then I'm going to work more carefully on the slope of the red line and the slope of the blue line in order to solve the rest of the problem. Okay. Now, So we've been told that the anodic Tafel constant is 0.075, and that has units of volts per decade. And so I'm going to multiply that by 2 so that it would be 0.15 volts per 2 decades, because that's just going to be easier for me to think about. And so if I let this value be negative 0.1 and this be negative 0.2, negative 0.15 would correspond to right there. And so over 2 decades, this would be 1 decade, this would be 2 decades. Over 2 decades, I want to end up at this at the same value of 2. In this case, it would simply be 2, actually. And so now I can now correctly draw the slope of the oxidation curve, and I am doing so. And you can see that it is approximately that. All right. So I'm going to repeat this process by focusing now on the reduction curve, and the reduction curve has a Tafel constants of plus or minus 0.10 volts per decade, so that'll be a little bit easier for me to draw. So over 1 decade, I simply go down an order of magnitude, still sticking with 2, and so now I draw a nice straight line going through those points, and I have the reduction curve. Okay, so hopefully this makes sense so far. I'm going to continue and kind of finalize the rest of the problem. So we want the metal oxidation curve to be reduced to a rate of 0.2 microamps per square centimeter as per the problem statement. So over here on the upper axis, that's 10 to the minus 1, which is 0.1. So 0.2 is going to be right here. That's going to be 0.2. And so that's the rate at which we want the metal to get polarized to. So we've already answered part of the problem statement. We're going to have to polarize the metal by that much voltage in order to reduce the oxidation rate that far, and that looks like a change in voltage of about 0.223 ish. And so that would be the amount that we need to polarize it. We need to polarize it that far down in order to reduce the corrosion rate from 2 times 10 to the 2 to 0.2 microamps per square centimeter. Now, how much current is needed? All right, so let's use red to kind of differentiate that. So the amount of current you need, you simply take the amount of polarization that you needed, and you kind of just read over until it intersects the reduction curve, and then you read up. Okay, so when we do that, read over and up, you can see that we end up at, this is 1 times 10 to the 4, that's 2 times 10 to the 4, this will be 3 times 10 to the 4th microamps per square centimeter. So that would be the amount of current needed, and that would be the answer to part A. This would also be the answer to part A. And let me just write A next to that so that we have a nice tidy solution. All right, so now moving on to part B, if concentration control takes over for the cathodic process at a current density of 3,000 microamps, so that would be 3 times 10 to the 3 microamps per centimeter squared, so that's 1 times 10 to the third, 2 times 10 to the third, 3 times 10 to the third is right there. So if at this current, what that's saying, and I'm gonna switch to the blue line, what this part of the problem is stating is that at this current, okay, the diffusion of whatever it is that's reducing is now limiting the rate of reaction, and so the sort of modified reduction curve now, and I'm going to crosshatch what it looks like, so it now follows this trajectory all the way down, and this part of the curve no longer happens. And so that's what that means for concentration control to take over according to the image. And so the question then is, what is the corresponding cathodic overvoltage and current required? All right, so the amount of cathodic overvoltage is going to be the same. All right, it's going to still be 0.223 volts because we need to be at this potential in order for that amount of metal reaction to take place. All right, so this also will be the answer to B. The cathodic overpotential is going to be 0.223 volts. However, what's true now is that we don't need as much current. We only need this much current, right? Because that's the limiting rate of reaction for the cathodic curve. And so, in other words, we need for the answer to part B is that we need 3 times 10 to the third microamps per square centimeter in order to reduce the metal oxidation rate to the value that we want of 0.2 microamps per square centimeter. All right, well, I hope that this has helped you understand how we can polarize a part and how much current is necessary to polarize a part in order to pull down the rate of reaction by orders and orders of magnitude. And so in principle, this technique can be used to protect any metal. In practice, it becomes a question of the cost of electricity versus the cost of the corroding part and the maintenance that's necessary in order for this to happen. And so with that, I'm going to wrap it up, and thanks very much. Bye.